All right, so welcome everyone for this colloquium. It's a pleasure for us to have here Professor Guido Boffetta from University of Torino, the INFN. Professor Boffetta is a specialist in turbulence, as you'll see today. He did his PhD in the University of Torino, has been a full professor there since 2011, right? Has had several visiting scientist or visiting professor positions, in particular a Fulbright position in Los Alamos laboratory. He's the author of over 100 papers in the area and also member of the editorial board of Physical Review Fluids. So you can see he's really a specialist. Many thanks for accepting the invitation, and please feel free.
Okay, thank you very much. So let me first thanks Luca Moriconi for inviting me here for a couple of weeks. I thanks also CAPES for the financial support. I think it's correct, CAPES. And then I also thanks Attila Freire for the hospitality in his lab. So today I will try to give, I was suggested to give turn up volume. I don't think we need, but I turn up, otherwise, okay. Do you know how to? Wow. Wonderful. So we'll try to give an overview on two-dimensional turbulence at very, very simple level, because I was told that maybe there are people that are not specialists in turbulence. So if there are specialists in turbulence, probably we'll find this too simple, a little bit, hopefully not too boring. So let me start with a couple of slides about turbulence. So what is turbulence and why we study turbulence? So there is a very famous stupid quotation by the turbulence is like pornography, in the sense that it's difficult to define what is exactly turbulence, but when you see a picture of turbulence like this one, you immediately recognize okay. But more seriously, is a classical nonlinear field theory, which starts from equilibrium, as we will see, with non-perturbative approach, very strong non-Gaussian statistics, and with anomalous fluctuations. So why we are, as a physicist, we are interested in turbulence? So turbulence, there are several examples here on very different scales. This one is a turbulent jet produced in the lab with a few centimeters in diameter. This is a Greek turbulence, which is a prototypical experiment with a size of about 10 meters, so very different size. This is the numerical simulation of Navier-Stokes equation, so there is not an intrinsic size here. And this is a geophysical flow that we'll discuss more in detail in the second part, in this part of the talk. But all these flows are very, very different scale, very different origin and forcing. But if you look at the small scale statistics, for example, the small red square here, what you get is there are some universal behavior. For example, the simple things you can look at is the energy spectrum, which is represent the amount of energy that you have at a giveaway number, and the energy spectrum in the intermediate scale at sufficiently small scale, or in all these cases, has the same slope, which is the Kohlberg spectrum with a scaling exponent 5/3. So it's scale invariant, and since it is scale invariant, it is independent on the particular flow they are considering. The reason why there is this universality is that all these flows are governed by the same equation, which is the Navier-Stokes equation, as you probably know. So let me remind you the Navier-Stokes equation for an incompressible velocity field. You can write in this way. So this is the viscous term, nu is the kinematic viscosity, and this F represents an external forcing that is needed in order to keep the turbulence going. Okay, so the idea of turbulence dates back to Richardson idea that was almost 1 century ago now, 26 if I remember correctly. Richardson made a lot of technical contribution to fluid dynamics. Also, is the first that invented essentially numerical weather prediction, Richardson. But he also wrote this very nice poem after Swift that is summarized the idea of what is called now the Richardson cascade. So you have a big walls, which means vortices, which are injected by the forcing. For example, in this previous example, the vortex here is injected by the jet when he exits the flow. So this is the big vortex that became unstable dynamically, so produce smaller vortices, which produce smaller vortices. So this is a scale invariant process. until you reach very small scale where the viscous term becomes important, and so it converts the mechanical forcing into heat. Okay, and so within this range, between the forcing and the dissipation, which is called the inertial range, you don't have any external forcing, and so the energy is simply transported by large scale to small scale. That's why it's very far from equilibrium, because you force the system at a very big scale, and you remove the energy at a very small scale. Okay, Then, if you don't have any viscosity, so you neglect this term and the last term, you have the Euler equation, the Vichy-Euler equation, which conserves the kinetic energy. Density is constant, so you can take density equal 1, so kinetic energy is nothing but U square average. Okay? And this is conserved by the Euler equation. Now, if you consider the Navier-Stokes equation with viscosity, you can simply compute it very trivial. You multiply this equation by U and you integrate, and you immediately get that the energy is dissipated now because you have viscosity at the rate which is proportional to nu times zeta. Zeta is called the entropy. It is the average of the vorticity square. The vorticity is the curl of the velocity, of course. Okay, so this is trivial. It's just from the Navier-Stokes equation. But then there is the first important fact of turbulence, which is called, if you want, the zero law of turbulence, the dissipative anomaly. So if you consider now the limit of very small viscosity, which is relevant for application, because in the normal unit, both water and air are very small viscosity. Okay, if you want to be more technically speaking, what you have to consider is the dimensionless measure of viscosity, which is the Reynolds number. The Reynolds number is the inverse of the viscosity made dimensionless. So this is a dimensionless number. You can think about, you can speak about the value of dimensionless number only. So in the limit of small viscosity or larger Reynolds number, you have the energy dissipation rate, so this quantity do not vanishes in the limit nu goes to 0, but you reach a finite value, epsilon, okay, independently of mu. And the reason, the physical reason, is that when you decrease the viscosity, your cascade extends to smaller and smaller scale, and so the entropy theta increase to compensate exactly the value of viscosity. So at the end, you have a finite dissipation. This is not a theorem, this is just empirical evidence, okay, from many experiments and many simulations, but there is no demonstration that it should be like this, in general. Then there are some results. Okay, so now the theory of Kolmogorov is based on the theory of Kolmogorov that I will summarize in one slide, describe this in the inertial range, so the scale between the forcing and the dissipation. And Kolmogorov was able to derive essentially a prediction for the velocity difference at a given scale. What is the velocity difference at a given scale? Means the velocity fluctuation associated to a given heading. No? You have a different heading, you have in mind, a different scale. You look at the statistics, delta U, between 2 points in your turbulent flow, because single point is simply Gaussian, there is nothing interesting there. For the Navier-Stokes equation, Kolmogorov was able to derive an exact result, which is probably the only exact non-trivial result that you can get from the Navier-Stokes equation, assuming essentially homogeneity isotopy, and then you have to assume that the system has very large Reynolds number, so the separation between the injection scale and the dissipative scale is very large. And so in the intermediate scale, he was able to obtain this result, that the velocity fluctuation at the scale r to the power 3 average without absolute value is equal to minus 4/5, which is a number, epsilon, which is this flux of energy that goes to small scale, times r. Okay? So this is exact. This is from the Navier-Stokes equation. Now, since this is a third power, the third power of velocity fluctuation, you can assume that the statistics is similar. And so if the statistics is similar, you have a scale, from this, you have a prediction for the scaling exponent of velocity fluctuation, which is h equal 1/3, okay? Because when you have third order moment, you should have something which is linear in R. And from that, you get exactly the Kolmogorov spectrum that we have seen in the experiment before, okay? This is very simple, but of course, this is not the end of the story, because this is not, the similarities violate the turbulence. There are a lot of experiments, again, and simulation that show that there is not set similar, turbulence is not set similar. This is a picture taken from experimental data. What we see here is exactly the probability density function of velocity fluctuation, delta U, taken at different scales in a turbulent flow. Okay, so the bottom one is for very large scale, close to the forces, so the big eddies, and the probability density function is close to a Gaussian. Okay, so this is a lean log plot, so the parabola is a Gaussian. But then if you go to smaller scale, the different lines are shifted just for clarity, okay, but they are all normalized to one. When you go to small scale, you see that the distribution is not Gaussian anymore. There are some large tails that develops, which means that you have a probability, relatively large probability to observe strong events, very large fluctuation of the velocity at small scale. This is called intermittency. It means that similarity is violated. You have not a single scaling exponent. And indeed, if you look at the scaling exponent of what are called the structure function, which is the generalization of Orff's law, so you look at the velocity difference to the power p, okay, you have a set of scaling exponents zeta p, which deviates from the set similarity. Set similarity means that this data should stay on the line p over 3, which is the continuous line. This is the Kolmogorov prediction. But the evidence is that there is a deviation as you go to higher order moment. Of course, p equal 3 is exactly equal to 1 because this is an exact result. Okay, but the other one there are no results that there are no constraint for the value of the scaling exponent for the other moments. Okay, so these two slides, I try to summarize everything about three-dimensional turbulence, so probably very, very, very fast. But now, why we are interested in two-dimensional turbulence? So, of course, one reason is that two-dimensional Navier-Stokes equations are one very simple, probably the simplest model for large-scale motion of the atmosphere and the ocean. Is very naive model. I mean, nobody uses reality Navier-Stokes equation to make the prediction or the ocean prediction, but it's a very simple model because both the atmosphere and the ocean has very thin layer of fluid. If you think of the Pacific Ocean, the aspect ratio is 1,000 or 10,000 kilometers times 10 kilometers. So it's very, very thin. And moreover, in the Earth, you have a stratification and rotation, which also suppress the vertical motion. So the motion in the atmosphere and the ocean at very large scale is almost two-dimensional. So this is one motivation to study two-dimensional turbulence. Then the other motivation is that to see which is the motivation for a physicist, what are the differences between two-dimension and three-dimension in general, and also in a turbulent flow. Okay, so the main difference is the following. So if we write the Navier-Stokes equation, again, here without forcing for simplicity, this is valid both in 2D and 3D, okay? But now let's write the equation for the vorticity field. So I take the curl of the equation, so I get this equation, which is for the vorticity field, okay? But now, in 2 dimensions, there is a big difference between this equation. This is valid in general, but in 2 dimensions, this term disappears. Because in 2 dimensions, the velocity is a planar, is x and y, let's say. So the vorticity, which is the curl, is in the zeta direction. And so this scalar product vanishes, identical. And this is very important term because this is what is called in 3 dimensions is the vortex stretching term, which is responsible for the direct cascade of energy. Okay, so the difference. So in 2 dimensions, the vorticity is a scalar. It's a scalar field, which is only one component, which is transported, essentially is transported by the velocity and dissipated by viscosity. So the consequence is that not only in the limit of Euler, so zero viscosity, not only the energy is conserved, kinetic energy as in 3D, but also the entropy, which is the vorticity square, since the vorticity is simply transported, also the entropy is conserved in 2D. And this makes a huge difference. Because now, if you consider viscosity and you write the energy entropy balance, so how they exchange with the fluid, so the energy, again, is exactly as in 3D. The energy dissipated at a rate which is proportional to nu time entropy. But now, in this case, the entropy is also dissipated at a rate which is proportional to this quantity, P. P is a paleistrophy. It doesn't matter, but it's a positive quantity. Okay, so it means that the entropy dissipated, so it means that the entropy is bounded by the initial value, cannot go, and so it cannot compensate a vanishing viscosity. So the consequence, just for this very simple argument, is that there is no dissipative anomaly in 2D. Okay, this is the big difference with respect to 3D. And this was already realized by Taylor more than 1 century ago, but Taylor also concluded that probably there is no turbulence in 2D. Of course, it was wrong, but it was able to show that there is no dissipative anomaly in 2 dimensions. Okay, so this is a very important result. And so what happens to the energy? So it takes some time to understand what is the fate of the energy in two-dimensional flow. And probably the first contribution was by Fjordov. Okay, in this picture, Fjordov is this long guy here. You recognize here from Neumann. This is Charney. So this is a picture taken in the 50s. There was the first experiment for weather forecast and numerical weather prediction at ENIAC. Okay, but apart of the picture, Fjordov was able to understand that, okay, now a little bit technical, but we don't need to follow all the details. Okay, you can write the energy balance, not globally average of all the space, but of scale by scale. So you take you take the equation, you multiply by you take the Fourier transform, and you end with the energy balance in Fourier space, which means that the change of energy, the given wave number, has three different contributions. One is the forcing, which comes from this. One is the dissipation, which is a negative, always dissipate energy. And these are the most important things, is the transfer term. These represent the energy that comes to y number k from the other wave number because of the nonlinear term. Okay? And this can be written as the sum of all the possible wave number which sum to k. It is really the transfer term. Okay? Now, because you have energy entropy conservation in the Vichy limit, the transfer term has two equations, two equality, must satisfy two equality, okay, which means that the energy and entropy are conserved. And now Fjordov was able to realize the following thing, to derive an inequality from these two equality. Very smart. So it takes if you take two different wave number, k, p, q, ordered, for example, in this way, so k is the smallest wave number, which means large scale, okay, q is intermediate, and p is small scale. From these two equations, you are able to show very easily this inequality, that the transfer from PQ to wave number K is larger than the transfer from the other wave number to wave number P. So the energy is transferred to large scale faster, more efficiently than to small scale. This is what the inequality represents physically. Okay? So the idea of Fjordov is that the energy, you inject energy in a system in two dimensions, it does not produce the direct cascade to small scale as Richardson predicted, but it has to go to large scale because to small scale it cannot be dissipated. This is simply why it cannot go there, because it cannot be dissipated there. Okay, and then after Creighton in the 60s and 70s, wrote a paper on two-dimensional turbulence, and it was able to derive essentially the equivalent of Kolmogorov theory for two-dimensional turbulence. Also, here I will go very fast, but from the balance equation, the one that we showed before, is stationary condition. So you put the force, you neglect time derivative because statistically you assume to be stationary. Okay, you can introduce what are called the flux of energy and entropy, which is nothing by the integral of the transfer term. And then assuming that you have a scale-independent energy flux. Why scale-independent? Because at intermediate scale you have neither forcing nor dissipation, so the flux the energy must be simply transferred. He obtained exactly the same scaling of Kolmogorov spectrum, but this is for the inverse cascade, to large scale. And while if you assume to have a scale-independent entropy flux, so the entropy is the one that's going to small scale, you have another prediction k to the minus 3. So apart the detail, the picture of Creighton is summarized in this picture, okay? So you have a system, two-dimensional system. This is the energy spectrum as a function of wave number. You force the system at an intermediate a given wave number, and so you are injecting energy, entropy, everything. And then you have that the energy is transferred to large scale, producing the Kolmogorov spectrum, but is an inverse cascade. So it goes to large scale. This energy is going to large scale, while the entropy goes to small scale, which is the second conserved quantity, goes to small scale and produces k to the minus 3 spectrum. Okay, then later I propose a logarithmic correction, but this is a technical point that we don't need to discuss here. It's also possible to extend the fourth law, the exact law, also two-dimensional turbulence, and then you get exactly the inverse cascade. You have the same scaling law. The third moment is linear in R because the scaling exponent is 1/3. But now you see, you remember in 3D was minus sign, the sign was minus. Here is plus because it's an inverse cascade. So simply looking at the skewness of the velocity difference, you have a signature of what is the direction of the flux, direct or reverse. That is very convenient for analyzing the data, for example. Okay. Okay. So this prediction by Creighton for the statistics two-dimensional turbulence can be checked in laboratory experiments. And so this is one of the classical experiments that people do with soap film. Soap film are very convenient because they are very, very thin, so it's almost two-dimensional. But of course, there are some difficulties, in particular the evaporation that limits the possible observation. And also the diagnosis is very simple. Two-dimensional turbulence in experiments is much simpler than three-dimensional turbulence because you have just a plane. So with the camera, you take all the velocity field, so you have everything, no? While in three dimensions, it's much more complicated. But it is difficult to study the inverse cascade because in order to study the inverse cascade, you need the forcing at very small scale. And it's difficult in a soap film to inject energy at small scale. And so more recently, some people from Spain, they invented this experiment, which is very, very nice, very smart. The idea is to have a very thin layer of fluid. They use oil or water. Okay, you produce Faraday wave by vibration, and this Faraday wave inject the energy, the entropy at a natural small scale, which can be a fraction of millimeter. So in this case, they were able to observe a very clear inverse cascade. So this red line here corresponds to the scale of the forcing, which is the wave number that you have in Faraday waves. And you see that the larger scale, smaller wave number, you have a very clear Kite spectrum k to the minus 5/3. Okay, this is for the experiments, but also what you can do is numerical simulation. That's what we do usually. Numerical simulation, you have to solve the Navier-Stokes equation in 2D, which in principle are much simpler than the Navier-Stokes equation in 3D. You have only two dimensions, you have only a scalar field, so you can push a lot of resolution. And so some years ago, together with Stefano Musacchio, we performed a set of simulations starting from 2,000 square to 32,000 square. And the idea was to increase the resolution because people had some difficulty to observe the K2-3 in the direct cascade. I will explain in a second. So these are the results of the energy spectrum, again, at different resolution, different run from A to E. Okay, and we formed a system of wave number 100. You see this peak is the forcing. You have an inverse cascade large scale with the spot scaling predicted by Kreischer, 5/3, and we observe a direct cascade with a spectrum which is steeper than K2-3, and this was already observed before. But what we were able to do here, increasing the resolution and decreasing the viscosity, so we are going to viscosity close to 0, we see that the spectrum is always steeper than K2-3, but seems to recover the prediction, the theoretical prediction. And indeed, if you compute the correction to the scaling law, just by fitting this line, you get that the correction seems to vanish as the viscosity goes to 0. So the indication here is that in the limit of infinite Reynolds number, you can never reach in numerics, but you can approach. The indication is that the Kite picture of the double cascade with the two scaling exponent is correct. Okay. You can also, with the numerics, you can look at everything, of course. You can look, for example, at the fluxes. So this represents, again, as a function of wave, wave number, the flux, so the transport of energy, and the entropy. And when you have a plateau, it means you have a constant flux scale by scale, which is what you expect to have in a turbulent flow. And you have a negative flux of energy, which means an inverse cascade, and the positive flux of entropy to small scale, which means the direct cascade. Okay, but apart of that, there is one point that I want to discuss a little bit more. Is the statistic of the inverse cascade. So the inverse cascade in two dimensions is equivalent in a mean field, for the point of view of mean field theory, to the direct cascade in three-dimensional turbulence. But we have seen that in three dimensions we have the breakdown of size similarity. We have anomalous fluctuation with the PDF which change with scale. This is not the case for the inverse cascade. The numerical evidence is that in the inverse cascade to two-dimensional turbulence is really self-similar. There is no intermittency correction, and this is the probability density function of the velocity at different scale, they collapse on a Gaussian. Okay, so it's something which is much more close to equilibrium, if you want, in some sense, at least from the point of view of the statistics. If you compute the Geiger or the structure function, this is more technical, but you see no intermittency. Okay, this is a big difference between the two-dimensional and three-dimensional. Okay. Now, there is a small intermission. I was not sure I wanted to discuss this, but I try to do very briefly because it's connected to what I said before, and maybe it's more interesting for a broader, for some of you. So we know from statistical physics that when you have a two-dimensional system, which is homogeneous, isotropic, a scale invariant, very often is also invariant under conformal transformation. So you probably know better than me what is a conformal transformation. Is a local scale invariant which preserve the angles. Okay, it's not a theorem because there are some counterexamples which are not conformal invariants. There are some models which have been shown they are not conformal invariant. But since two-dimensional turbulence in inverse cascade is homogeneous isotropic by construction, and we have seen that this scale invariant, so there is not intermittency, it's natural to ask whether it is also conformal invariant. Right? We were not the first to ask this question. Already Polyakov in the 1990s investigate this problem but only from a theoretical point of view, and he concentrated on a direct cascade which is not conformal. Okay, so we studied this problem from a geometrical point of view using the powerful technique of the stochastic linear equation, and I will just to show you a couple of results because I think it's also very nice to look at the result also from an aesthetical point of view. Okay.
The popular examples, do you bring some other
I'm not sure about the 2D elasticity. Sorry, I don't remember. But we also were able. I will show you if you want. We are also able to show in some regime in which two-dimensional Navier-Stokes equation is not conformal invariant. Okay, this is not local. Of course, it's not local in our case, but normally it's conformal invariant, but we can break it with a small trick. Okay, so what we did. Okay, so we take the vorticity field. You remember, no, the Navier-Stokes equation in 2D is a transport equation for one scalar, which is the vorticity field. So this is a typical snapshot. Okay, the resolution here is not very nice, but you can recognize this color represents the value of the vorticity. So you have vortices, you immediately see blue and red, like cyclone and anticyclone. Okay, positive and negative. Green represents close to zero vorticity. Okay, so this is it is dynamic. This is just a snapshot, but then evolves in time. Okay, according to the Navier-Stokes equation. So then we apply one of these standard things to identify the region with the same sign of vorticity, or the scalar field omega. So what you get is this. This is exactly from the picture that I showed below. So it is a kind of clustering in which you observe the cluster, each color represents a cluster of vorticity with the same sign, in this case positive. Okay, some of them are very small, some of them are very big. Okay, and if you look carefully, you see there is a lot of black region. At least, indeed, one half of the picture is black. Doesn't see because this is only positive vorticity. So there is also the negative vorticity. Then you can play the game with no negatives, the same as in meter. The average is zero.
Dissipation does not break the scale invariance.
Thank you very much. Viscous dissipation. So dissipation in general breaks the scale invariance. So we are interested only in intermediate range of scale. Also forcing breaks the scale invariance. No? Any scale you put in the system by definition. But the idea is that when the resolution is high, you have a very large separation between forcing and dissipation. And in between the two, you assume to have a scale invariant. You observe scale invariance if you look at the spectrum and the structural function. Okay. Thank you very much. It's not indeed conformal invariant is only also conformal invariance is only in a final range of scale. You cannot assume in all the scale.
Energy removal mechanism.
A large scale. Yes, I didn't want to discuss this, but I will discuss a little bit later if you want to. If you want to be stationary, yes, the question is very simple. No, it's very smart in the sense that if you have an inverse cascade of energy, the energy goes to large scale, and there is nothing that dissipates this energy because viscosity is a Laplacian, so it's acting on a small scale. If you want to have a stationary solution, you need to put some additional, some mechanism that removes the energy at large scale. In the experiment, this is a typical friction. Friction from the bottom, the friction is an interaction between the fluid and the three-dimensional world, if you want, no? Which is the friction with the air, friction with the bottom. In numerical simulation, you have to add this friction by hand if you want stationary solution, but you know, maybe you don't need. I mean, I will discuss a little bit more about this. Here is each one is a cluster, which means a connected region with positive vorticity. Positive, but you can play with negative. It's the same, absolutely the same. But you cannot do together because otherwise it cover everything. So it means that this yellow is disconnected by this red, and in between there is a negative. Okay?
So it looks like not too easy because the black regions.
Yeah, looks the black region is much smaller. I think there are two effects. One is a lot optical illusion because it's black, you see less. And the other problem is that the boundary between the two is color instead. It should be at the 1/2. I don't know, but this is. The color coding is not color coding. Each cluster has a different color at random. It's just to see what are the clusters. So this small yellow here means they are all connected points with the same, with positive vorticity. Okay? Some of them are small, some of them are very large. Okay? But what you see here immediately, they are not smooth objects. They are kind of fractal objects, no? Let's concentrate on one of these objects, which is more clear. There are a lot of fjords, lakes inside, so it's really not a fractal object. So you can start computing, for example, the fractal dimension. The fractal dimension, not of the cluster, because the cluster is two-dimensional, because it covers a surface, but the fractal dimension of the boundary, the cluster, okay? And so this is what we did. And this is the fractal dimension of the external boundary, okay? Which is, okay, in this is one of these clusters. The external, the full boundary is represented here in green. So green corresponds to red, red corresponds to blue. I'm sorry for this color coding, which is not very, was not very stupid. Okay, so if you compute the fractal dimension of the boundary of this cluster in the inverse cascade, you get some scaling law. So this length as a function of diameter, so the slope means the fractal dimension. And you get a dimension which is very close to 7/4. Okay, this is not a fit, 7/4. It's a number that I will tell you where does it come from. But you can also compute the fractal dimension of the external boundary. So you remove all the fjords that enter in your state, which is represented here by this red line. So it corresponds, this is an example that you know very well. No, you close all the fjords, you close the fjords, and you compute only the external boundary, which can be reached by infinity without cutting the cluster. This is how it's defined. And you get an exponent which is 4/3. Okay, and then you compute some other statistics I don't want to discuss. So these numbers are not magic, but are the fractal dimension known in critical percolation. Critical percolation, people know that the cluster of percolation, which are the percolating cluster, have exactly the same, this scaling exponent. So this is a suggestion that is something to do with critical percolation. You can do something more, for example, not only a single cluster, but you can compute the distribution of the sides of the different color, of the different cluster. And if you have enough statistics, you get this distribution, and you see that you have a power law distribution for the sides of the cluster, the sides of the boundary, which fit very well this strange exponent, 96/91, which is a crazy exponent, but it's something which has been computed for critical percolation. So the indication is that the inverse cascade seems to be geometrically at least equivalent to critical percolation, which is one of the simplest, probably the simplest system of critical phenomena. And so I will go very, very fast here because I cannot tell everything, will be another seminar. But in order to check this hypothesis, we use the mechanism of stochastic low-energy equation. If you know, probably you know better than me. If otherwise, I will try just to give an idea of what is it. A very powerful method in which people use it to compute a lot of critical exponents, a lot of results, mathematical results on critical system. Okay, and the idea is that if the boundary of your cluster, this green line, is conformal invariant, then it can be mapped by this low-energy equation, which is a map which transforms the plane in itself to a Brownian motion. If it's a conformal invariant, this driving function is called the function, has to be a Brownian motion, and the only parameter that you have is k, which represents the diffusivity of this Brownian motion. And the different diffusivity characterize the different fractal dimension, but characterize the different class of universality. Okay, and in particular, critical percolation has k equals 6. Okay, this is the exact result. So we apply this low-energy equation. Okay, cannot enter in the details, but we apply to all the cluster of the boundary of our cluster in two-dimensional turbulence. Each one produce one of these. You see, this is a Brownian motion, one realization of Brownian motion, different realization, and then you average. You have the variance. If it is a Brownian motion, the variance grows linear in time. Okay, and you get exactly a Brownian motion. You can compute the diffusivity by compensating with t. and you will get something which is very close to 6, 5.9 plus minus 0.3. Okay, so this is the direct indication. The cluster of vorticity in the inverse cascade are equivalent to critical percolation. And then after that, several people look at other two-dimensional turbulence systems. They found similar results, but not in the same universality class. You see that all these systems, as far as I know, all the systems with a standard range of inertial range, standard inertial range, are conformally invariant, but with different value of diffusivity. Oh, okay, so let me, how much time do we have? Okay, all right, so, sure.
When you compare the problem with this CT with the problem in motion, in the problem in motion, are you supposed that there is stepwise Markovian or not? Compare this equation with the problem in motion.
Yeah, for by the
has force there.
the Brownian motion is Markovian by definition, sure.
Exactly. Well, is this system Markovian or force not?
No, sure.
Where is it? How can you compare something which is Markovian to something?
Okay, so first of all, here time is not the time in the simulation, okay? So what do the Stochastic-Loebner equation, it transforms theta, which technically belongs to the complex plane, it transforms in a because it's conformally invariant, you can compress, if you want, on a linear function, of a scalar function of time. And time geometrically represents one of the two directions along the line, okay? So it's not the normal time. Okay, what means Markovian here? K equals 6 has an important property that, in particular, that the statistics that you have in a cluster do not depend on the neighbor of the cluster. So you have no memory along this, the boundary in this case. And so in this sense, it is Markovian. Okay, but it's a geometrical property, not in time. Thank you. Okay, so let me go back to more physical and classical picture. So let me go back to the inverse cascade now. Okay, so we have seen that in two-dimensional turbulence, the energy is connected to the question that you asked before. In two-dimensional turbulence, the energy goes to large scale. Okay, and so the question, the natural question, what happens to this energy? Where is it dissipated? What is the fate of the energy? Oh, sorry. This was already discussed by Krachan in the original paper. And so the idea is that as the energy is transferred to larger scale, eventually we reach the maximum scale, which is the box size, the size of your simulation or your experiments. And then it cannot be transferred to larger scale because they do not exist. And so the energy starts to be accumulated at this scale. This is a movie of, you see the spectrum as a function of wave number, it's a function of time. This is a real simulation. This is just the beginning. This spike is the forcing. You are getting the energy there. And then you see that the energy is transferred to large scale, develops, this is the scaling, the Kolmogorov spectrum, k to the minus 5 term. And then eventually you reach wave number 1, which is the largest wave number we have in this simulation. And so the energy starts to condensate, they call. Okay, the condensate is a name in a similarity with the Bose-Einstein condensation, but I think it's not, of course, there's nothing to do, it somehow is also misleading, but in any case, now it's called the condensate. A condensate has been observed not only in numerical simulation, but also in experiments. These are nice experiments by Schatz and Colóquio. So this is from a water tank. You see, this is the Kolmogorov spectrum. This is a very huge compensate. There is a lot of energy at a smaller wave number. So the condensate corresponds to the fact that in the spectrum you see a peak at the larger scale because the energy starts to accumulate there. So, but what is the condensate if you look in the real space, no? So I want to show you another movie here, which is very simple, but probably nice. So this is a simulation of the inverse cascade as it proceeds in time. And you will see the formation of the condensate. This again is the vorticity field, but now yellow and blue are positive and negative, or vice versa, doesn't matter. And red is close to 0. What you see here is not the vorticity, this is the stochastic force, which here we are at time 0. So this is the forcing that you impose at time 0. The scale of the forcing you see from this difference to the distance, okay? And it's random in time, so it changes every time. And so we start the simulation. Okay, the simulation starts. You see the formation of these small vortices. Okay, positive and negative, and dynamical process. And then you remember the spectrum. The spectrum moves to larger and larger scale. You don't see larger vortices here, but if you look carefully, you see there are kind of collective motion in which the small vortices is organized in large scale motion. This is how the inverse cascade proceeds in physical space. They organize to produce large scale velocity. Okay. Okay, the simulation is very, very long, and then, so let me skip a little bit, but when you go a very longer time, and this doesn't stop, you see the appearance of the condensate. Now we have already the condensate. If you look at the spectrum, there will be a peak, okay, when under one. And the spectrum, what is the condensate? It's nothing but the presence of two big vortices you see here, one positive, one negative, because the average must be 0. And this is simply the condensate, the formation of two large-scale vortices in the field. Okay? And at the end, the velocity field, the average velocity field, can I move this one? The average velocity field is very, very... Okay, doesn't matter. I don't know why I cannot... Okay, no, I was here. I wanted to show a later time. Okay, a later time, the mean velocity field is very simple. You have a dual point, and you can also see any parabolic point somewhere in between here. Okay, so the mean velocity field is very simple. Okay, this is one example. There is not universal condensate. There is kind of zoology of condensate because it depends on the interaction between the cascade and the boundary. So if you change the size of the box, you have different shapes. If you change the boundary condition, this is from an experiment. So there are no slip boundary condition, while in our case is periodic boundary condition. So with no slip boundary condition, instead of two vortices, usually you have a single vortex, which break the symmetry up and down. This is another example. So there is a zoology, but since the velocity field inside the condensate is very simple, it's just a mean flow rotating velocity plus some fluctuation, is it possible to make some analytical prediction, very simple, starting from the momentum and balance equation? We go very fast, but using polar coordinates, you assume that you have only azimuthal velocity, the mean velocity, which rotates around the melting point. The radial velocity, the average radial velocity is 0. Then you have some second order term because of the nonlinear term, but you can use a kind of perturbative approach here because the fluctuation with respect to the mean velocity is okay. So you can close the equation, and you had at the end a very simple prediction that inside the condensate there is a universal vorticity profile, which indicates as 1 over R. And this number here is just, it's not, there is no free parameter here. Everything is fixed by the physical number. And okay, from the simulation, you see that this prediction works very well. Line without free parameter again, but only inside the condensate. So you see this is 1/10 of the box size. Is that more or less the size of this Y? Depends on the boundary, depends on boundary condition. So if I have still another 10 minutes, I can now move to the second part, but it will be much shorter. And it's what about the transition between 3D and 2D? So we have seen that in 3 dimensions, the energy flow to small scale, in 2 dimensions goes to large scale. What happens in between? Is it possible to study what is in between 2 and 3? In which sense? Okay, there have been several discussions about what is between 2 dimensions and 3 dimensions, also from a theoretical point of view, but I will take a very, very simple approach. So the approach is to study what is called thin layer. So we study a layer of fluid which is very thin. So one dimension, let's call it zeta dimension. There is no gravity, so here it's independent. So, but zeta dimension is much smaller than the horizontal one, the vertical one. Okay, so you have different scale in this system. You have the horizontal scale, which you can take to infinity because you don't want to care about that. Then you have the viscous scale, okay, which is where everything is dissipated by viscosity. Then you have the forcing scale, which is where you inject the energy. We assume that this is localized in wave number, as usual. Then, okay, you have the thickness. L zeta. So when the thickness is smaller or the order of the viscous scale, you have by definition that all the vertical motion are suppressed by viscosity. And so in this limit, you expect to be in the limit of soap film, essentially, so two-dimensional. Okay, it is very clear. When the thickness is very, very small, smaller than the viscous scale, everything is dissipated in the third direction, so you have a soap film, essentially. Okay? On the other hand, when the thickness is larger than the force scale, you have a layer of fluid in which you inject energy at the scale in which the flow is three-dimensional. So there is nothing that prevents the energy to go to small scale. So this limit you also see when it is three-dimensional. So direct cascade. So this is inverse cascade of energy, direct cascade of energy. So the interesting point is to investigate what happens in between. When the thickness is larger than the viscous scale, but smaller than the friction scale. How is the transition between the direct and the inverse cascade? Is a discontinuous transition that the energy flux suddenly reverse? So first order transition or something continuous? Okay. And so we investigate this problem. We not only me, several people investigate this problem. And these are results taken by a nice paper by Giovanni Musacchio Vincenzi many years ago. So what I plot here is the energy as a function of time for different, so the key parameter, S is the thickness divided by the force scale. So this is a dimensional measure of the thickness. Let's call the dimensional thickness. So they perform simulation for different ratio, for different thickness. Okay, so thinner and this is thicker. What I plot here is simply the energy as a function of t. If there is an inverse cascade, the energy keeps growing because it's transferred to large scale. If there is a direct cascade, lies in 3D, there is a dissipative anomaly and the energy becomes constant. Okay? And so this is a very good diagnostic to see where is the transition. So they were able that for small thickness, you have some inverse energy cascade because the energy keeps growing. If you increase the thickness, the energy going to large scale is reduced continuously. And eventually, when the thickness becomes this number, 1/2, you have a constant energy, which means that there is no direct inverse cascade anymore. So if you want to summarize the function of the thickness, very, very small, you have a 2D phenomenology. Here from 1/2 on is three-dimensional phenomenology. And in between, you have a smooth transition. It's not a zero, it's not a first order transition, it's something continuous in which part of the energy, in this case, part of the energy goes to large scale, but the remaining part of the energy goes to the small scale. So what is called the split cascade. You can. Okay, thank you very much. No, in this case, very simple. We have a fully periodic boundary condition in all the directions. So it's sufficient to have because the thickness are pressed, there are no moles large scale. So this is, yeah, you can also play with the boundary condition, but it's more complicated. Okay, so we can look at the first thing you can look at the flux for understanding the split cascade. So again, these are the energy flux. Remember, this means the inverse cascade is negative and larger than the force scale, and this is a direct cascade. And so you see that increasing thickness from 1/A to 1/2, you have that the inverse cascade is suppressed and the direct cascade. So interesting to see how is the flow for intermediate scale S. For intermediate S, like 1/4, in which you have about 1/2 of the energy that go to small scale, 1/2 to large scale. So if you look at the spectrum, this case you see very nice, very weird spectrum, if you want, at the end, at the beginning. So this is the energy spectrum, very large resolution. So you plot the system here, that is one number. Inverse cascade of energy with probable spectrum, direct cascade of phase to with k to the -3, and then when you reach the thickness, the scale, the flow becomes three-dimensional. So from that on, you get again the k to the -5/3, but this is three-dimensional. So this is a direct cascade of energy. So the energy of the cascade is converted into energy producing three-dimensional. And this the relative weight of the two depends on the value of S. Okay. So since we have seen at the beginning that the main difference between, from a formal point of view, the main difference between three-dimensional and two-dimensional turbulence is the number of initial invariants. In three-dimensional, we have only the energy. In two-dimensional, the energy, the entropy. Okay. Or if you want, remember, no, look at the vorticity equation. In 3 dimensions, you have this additional term, which is the vortex stretching term. In 2 dimensions, you don't have simple. Okay, so the idea is, does this play any role in order to understand the split cascade? So the suggestion is that the split cascade in a thin layer, in this situation, even if the flow is principally 3-dimensional, at large scale, the 3rd dimension is suppressed dynamically. And so it means that if you consider the equation at large scale, you have not this equation. So the vortex stretching term is suppressed, and you recover at large scale a kind of 2-dimensional equation. And this can be measured. This can be measured by looking at the entropy flux, because if you have a 2-dimensional like phenomenology, you have the conservation of entropy. So this term disappeared. Otherwise, in 3 dimensions you have. So we computed here the entropy flux and the entropy production. These 2 terms essentially correspond, the entropy flux to this term and the entropy production to the vortex stretching. Okay? And so you see that a scale larger than the thickness between the force and thickness scale, the entropy production is suppressed. This is present in the equation. You have in the equation, but dynamically is suppressed. Is very close to 0, so you don't see. And you have a constant flux of entropy, which corresponds to the 2-dimensional cascade. And then when you go smaller than the thickness scale, so the motion becomes 3-dimensional, the entropy production, so the vortex stretches start to play a role, and so the entropy flux is not constant anymore, and you have a 3-dimensional. So the interpretation is that in the thin layers, at large scale, the entropy production is suppressed because of this mechanism. And okay, so this is the end of the talk. So thank you very much for your attention. And if you want to have some more details, there are some. Thank you, Guido. I hope it's correct. Google Translate.
It's perfect.
Obrigado.
So there's been a few questions during the talk.